that's a spin-spin correlation function. So it's only averaged over, a couple hundred Monte Carlo steps. But you can basically see it's exponentially decaying at that temperature. So, wait, what's J? Yeah, so that, as far as I know, this is this model, the one I wrote yesterday or on Wednesday. So those are just the thetas, theta I minus theta J. There's a button here that says show and hide vortices. Let's try it. I'm going to explain what a vortex is. Let's just look at them first. So this is what we're going to talk about today. A vortex will be a configuration that maybe looks like this. Okay? So it's some sort of topologically non-trivial object. Let's see if I can see any vortices. So I think the blues are a vortex. And they actually look different. There's different looking ones. Okay, and I'll explain why. Yeah, so this is like a vortex. It has a different charge or a different winding number than the one I drew here. The red is what's called an anti-vortex. So there's vortices and anti-vortices. And at this temperature, which is, what am I at, 2? So this is T over J. That's T in units of J. Basically, this is a paramagnetic phase. And just because everything's fluctuating, and the spin-spin correlation function is this really strong exponential decay. So let's lower the temperature. I think what I want to do is this. So let's lower the temperature to, I don't know, 0.5 and reinitialize. Okay, so qualitatively different. There's still vortices and anti-vortices. Let's let it run for a minute. You can see that the thing's trying to order somehow, but there's definitely defects in it. So those vortices are kind of stuck, and you can see there's two pairs. There's a vortex and anti-vortex pair. And they're separated by pretty long distances. Those two are getting close. If they get close enough, they'll annihilate. And I'll explain why later. So what do you think about that spin-spin correlation function? It's definitely not exponential, right? Oh, those two just annihilated. Oh, those two are there. They're all gone. There's now no vortices in that. It's still not perfect in terms of, it's not a perfect ferromagnet, It's not perfectly ferromagnetic. It hasn't spontaneously chosen, one direction, but basically, lots of this is pointing in a single direction. So the Goldstone, this is like there's a preferred ordering direction. So you're in this regime, this low temperature regime, where maybe if you measure the order parameter, actually I think if I stop this, will tell me what the magnetization is? Well, okay, the magnetization has finite numbers. I'm not sure what they mean. But, you're somehow in this regime of the double weld potential. And, if this thing had just picked a single direction for ordering, then you would have also ordered the angle, right? So this is an O2 model, so those variables are really describing, in some sense, the Goldstone mode. Let me warm it up a bit. Let's keep this configuration and go up to 0.89. Actually, let me stop it. And 0.89. So I've started from a new random configuration. This 0.89 is the value of the Kosterlitz-Salas transition for the 2D XY model, 0.893. So that's TKT. We're going to define that today. TKT over J, 0.8.
So this is the temperature at which they're supposed to unbind.
Yep, this is the binding or unbinding transition.
All right, I have a question about that. I was trying to understand what is actually meant by unbinding. Because I read in different sources, different description, and it's all kind of vague.
I'll explain it. There's a logarithmic, there's like a Coulomb potential.
Yeah.
So it has to do with that. So we'll learn. I don't know if I'll get to it today, but so qualitatively, what's happening at this temperature, I mean, you can kind of see it here, is vortices are occurring in bound pairs, is one way of thinking about it. If you go too low, like in temperature, they're basically confined in the sense that they'll never even get like one lattice spacing apart.
But
So
at this temperature, they were supposed to be unbound, so why are they supposed to be?
well, it's just a finite size effect.
Okay.
I mean, this is the thermodynamic critical temperature, 0.893. So you're just very close to the critical temperature. If you go much higher, I don't know how much higher you have to go on a finite size system, but then so I've kept the same configuration. Now I've raised the temperature, and I think those vortices, maybe they'll start drifting apart. The problem with these Monte Carlo simulations is you kind of get stuck in the configuration. The move, the Monte Carlo move, which is the angle twist of these things, is, I don't know what that, 6.28, maybe that's degrees. So they're only attempting sort of finite. If you stop this, maybe initialize it and start it again. 2 pi seems weird, right? So I don't know what it means. So here I've initialized it at a random configuration, started it again, and now more vortices will be in it at that temperature. And that should be approaching exponential now, so 1.2. So we're going to derive all these things. So yeah, the point is these vortices can be created in pairs and drift apart here in some sense, and they're deconfined, they're not stuck together. If I lower the temperature and keep this configuration, so if I just quench this down to a very low temperature, I'm not sure what'll happen. But energetically, the vortices will want to bind together now. So they might not be able to do it because what I would call ergodicity in a Monte Carlo simulation. But I don't know, maybe you can convince yourself that but if you stopped it and then reinitialized it at that temperature, then you'll quench down into one of the minima, the kind of rough free energy landscape that has very few vortices. So these ones want to bind together, but they're kind of stuck. Yeah, okay. So then once they find each other, they annihilate, and they basically never come back. And another thing is, it doesn't matter what I make this. Let me make the temperature slightly bigger. The spin-spin correlation function below the transition will always be algebraic. So that's different than things we've seen before, because usually we have power law correlation, decay of correlations precisely at a critical point, right? That's the whole point. It's exponential on either side of things, and it's only algebraic right at a critical point. I've just done 2 different temperatures, 0.5, 0.6. Okay, they're essentially vortex-free with some, I guess you call it long wavelength fluctuation for the Goldstone modes. But that spin-spin correlation function is algebraic even at this temperature. So if I ran a simulation anywhere from well, T greater than 0 to T.893, and it was thermodynamically large, that spin-spin correlation function would be algebraic, and then above that temperature it would be exponential. Okay, so let's derive that spin correlation function analytically from the XY model. And then we'll look at the form of it, and then we'll look at the idea of these vortices, okay, which are popping in and out of existence, but really only become, what if I make this huge? Really only become energetically favored at high temperatures. Here you're kind of ergodically stuck. I don't know if you change this angle. I haven't fooled around with this much. I don't know. It just looks like a mess now. This is a really high temperature, so. And that's a really strongly exponential decay of the correlation function. Enough fun. It's not what this class is about. Oh, shit. Okay. What was that correlation function? How do we calculate it? Okay. So, like I mentioned last time, you can think of either the action from the nonlinear sigma model, or you can think of this microscopic model. I like the microscopic model. The only thing you have to be a little bit careful about going forward is that the microscopic model is not defined within, a distance smaller than A, the lattice spacing. That'll actually save us in the end. Those thetas came from, remember I have Sx and Sy components. So let's just calculate the spin-spin correlation function, which I'll define like this. S x equals 0. Okay, so especially if you have periodic boundary conditions, you're translationally invariant, you just pick it's like ij. You pick I to be distance x, and j you can pick as the origin. So this will be the expectation value of these theta variables. That's what we want to calculate. And I'm going to do it, so I'm just going to sketch out how it works. We'll do it by writing the cosine as the real a part of an exponential, and then doing a Gaussian integration. So let me write these two exponentials like that. And I won't show it, but you have, for a random variable, so we're basically taking a Gaussian expectation value, which I can be more clear about. So what does that expectation value mean? So it's e to the I, let's write it like this, theta x minus theta 0. Right, so by definition, that's something like the functional integral. Right, so that's the expectation value we want. It's 1 over z, so we need e to the minus s theta. Right. Where that would be my Gaussian Hamiltonian. I guess I've written it as h there, but it's also the action from the nonlinear sigma model. Okay, so if there's one thing we can do, it's Gaussian integrals. This one's special. Well, this one's easy. It'll turn out to be this thing's squared. Right. So look at the cumulant expansion that we've looked at in this class. And in this type of Gaussian integral, any cumulants of order higher than 2 vanish. So this is the only thing that'll remain. So what we're left with is the expectation value of this thing, basically. And then we can exponentiate that. I didn't prove this. So you can convince yourself. So we need no. Right, this 0. So, because we're taking an expectation value, this simplifies. We have 2 of these terms that are squared. And when they occur by themselves, who cares what the position of x is? Right? It's just arbitrary. So these 2 terms are the same. So we have basically 2 theta squared. And then this term, nothing you can do with it. But we can pull that factor of 2 out. So 2. X is arbitrary, so let's set it to 0. But this one has the difference, so it's theta x, theta 0. Right. Good.
Sorry, I didn't get the cumulative expansion. So we have expectation value of e to the power of I and this difference. So this should be e to the power of expectation value of the difference minus 1/2 difference of the expectation value of the operator squared minus the expectation value of the operator squared outside. So that's the second order cumulative formula. So you see cumulative order higher than 2 vanish, but where's the second?
This one doesn't vanish.
Am I 1/2? And maybe there something is canceling out, but I can see right now.
So there's a cumulative expansion, you got to expand the exponential.
Yeah.
I didn't bring, we did this a while ago. So you expand the exponential, you have 1/2. That comes from the Taylor expansion, I think, right?
No, but when you have 1/2, then you have the operator, which you have there in the exponent, like your exponent. You'll take the expectation value of it squared and subtract the expectation value of this operator with a square outside. And this is the second cumulant.
Right.
And what you have here is something in between. It's like one part of the second cumulant.
It's like you don't have the connected, it's not the connected part. You don't have the...
What happened to the first order cumulant?
I think the first order part, okay, I didn't bring my notes. I think the first order part cancels either the connected part that I'm missing from, or... Okay, yeah, okay, I just wrote it. I didn't actually work it all out, but... Exercise. What I'm worried about is if I drop that I or not, once you started talking, but
yeah, I also wonder about the I and
I think I dropped it.
Because the 1/2 should be from the second cumulant, otherwise why should it appear?
Yeah, that's where this is from. I think there's still an I there. Because in the end, I got to drag around an I.
Oh no, you squared.
Yeah, that's right. That's where the minus sign comes from. That's where the minus sign comes from, yeah. And another thing is I'm dragging around the real part at some point too. I'm not sure if that matters or not. Okay, so I didn't write this all out and I don't want to do it, but I assume that that's the right form because it works on my page 5. So, but yeah, it's worth I don't think it's all that trivial. We did the cumulative expansion, but we were calculating the expectation value of something that wasn't Gaussian. So it's a Gaussian expectation value of something that had higher order terms. And then you have to be really careful in everything. You have to be careful to keep track of every term. In this case, as far as I know, all you can do all these Gaussian integrals, which only give you this contribution. So yeah, I should have been more careful. But it's too late now. So let's keep in mind that we're just looking at the real value, because now I'm worried about that. But okay, so I have this piece. Okay, so I have this thing here. Okay, so what I need is the Gaussian expectation value of that. So it's like I need to know the Gaussian propagator, basically, in the language of the field theory that we developed, right? So then this will be something like, we could do this in K space, which is simplest, maybe, with two momenta. And we have two fields of different momenta. And we need 1 minus, because that's the 0, 0. So we need 1 minus e to the minus or plus. I'm going to say plus. I k dot x. And we need to assign, say, k1 to that. It doesn't matter, either 1 or 2. So we would need to know this is like the Gaussian propagator, right? That's how we would solve this. There's probably easier ways. And in the ON model, this is where your delta function comes from that restricts your momenta, remember? So if I have J, then it goes here. And remember, the Gaussian propagator is just 1 over momentum squared, and then K1 plus K2. Or J is equal to rho S in the action S theta. So the Hamiltonian in the action I'm treating as the same thing. I can't remember why I used rho S. It's probably because this will be this spin stiffness. Yeah, this is the spin stiffness on your homework assignment. Okay, so maybe this is a complicated way to do this, but this is what we've been doing. This is how we've been doing these integrals, or these expectation values. And so then the delta function just restricts I'll write it here, us to 2t over j. K1 is equal to K2, which I'll call K, 1 minus e to the I. So now that's just K. Over K squared.
Do you really have those brackets within the integral? So you go from the expectation value, then you write it out in the integral over k.
Yep.
And so you.
So I have an x. I have two fields in each term.
Oh, you have transforms.
Yeah. I have two fields in each term, so I need two thetas. And in one case, so I Fourier transformed it, and in one case I have a distance defined, and in the other case they're both at x equals 0. So that's your unity there. I'm skipping so many steps that maybe I'm screwing this up. But it looked easy on paper.
No, I think it's okay. I didn't
think
notice
it's okay,
that there
yeah.
was a Fourier transformation. Now
Yeah, I just did the Fourier transformation because I know the form of this propagator in K space, right? We've already calculated this several times. So I just want 1 over K there. Let's see if this is working. So now okay, that's just the propagator. Mm-hmm. One minus e to the I kx. Oh, I start calling it r. K dot. Nope, this is my j here, sorry. Oh, I just wrote the same thing twice. Oh, okay, I think I screwed this up here. So this is my first term, and my propagator should just have, the delta function is just defined as this, right? Is that better? It's just a Fourier transform. The definition of the delta function. K, and I've set K1 equals to K2. So for the cumulant, and then I have that unity term that comes from theta squared. So it means my delta function, restricts me to that x equals 0 term here. Oh, that's what I get for being sloppy. This should be right, because this looks like 2t over j. Now this, I have 4 pi squared. And I can do this integral. I take out s of d, which is the angular part, which is just the integral over, I guess in this case, I only have an angle in, say, phi, call it. And then I have the radial component of the momentum, right? So I'll give it a cutoff here. So it should be dk. Then 1 over k. And then 1 minus e to the I. And what I'll do is I'll take the dot product of k dot x and call that kx cos theta. Okay?
in the step where you wrote K1 equals K2, what did you do from the, so you wanted to rewrite the delta function in the form of an integral.
Yeah, so here I want,
Delta function in K space would be an integral in
x,
an x.
right? You have an x integral that constrains, yeah, I skipped away too many steps, didn't I?
Well, I'm not sure about
So-
before, but I'm trying to understand this.
So the delta function gives you, this term here should give you that unity, right? And then this is the only term that has spatial dependence here.
Yeah. So, what is it? What was it supposed to be like? The step from the delta function to the next line where you have an e to the power of ikx.
Yeah, I'm trying to see where the. So when you integrate the delta function, and let's see. So when you integrate a delta function over x, right? And you have e to the I kx. So it's usually, it's like x minus 0 then.
If you integrate
so-
over
so
x, then you have a difference between k's.
Right, so yeah, so generally you have k1 minus k2, say.
Yeah, times x integrated over x will give you the delta.
Yeah, that's a delta function there.
That's, with 2 pi, whatever.
Yeah, whatever. I wouldn't trust the 2 pi's at this stage since nothing else is working.
Well, that's because of the 2 pi. Okay, so yeah.
Yeah, so that's your x integration, and so that should give you, I think that should constrain you. Oh yeah, so that's what gives you k1. At some point you're gonna have, that's where your k1 equals k2 comes from, right? It's flooding back to me now.
Like if you have it in this form k1 minus k2, then it will give you the result that k1 equals k2. In this case, you want to go back from the delta function with the sum.
Oh, so you have one delta function for every field, right? So you have two k's.
Yeah.
Like you have to have two Fourier transforms, right?
Yeah.
So the point is, yeah, so you have k1 minus k2. One comes from each Fourier transform. I mean, it's k1 plus k2 here. Yeah. That gives you the delta function here. Yeah, so I'm just going backwards, right?
No, but by going backwards, you're introducing the integral over k? Or where does the integral over k and k? Or how do you relate k to k1 plus k2? Is it just this? No.
It seems so easy at the time. Let's see, usually.
This is the only step. Maybe there is something. This
is the only step, but like I skipped a whole bunch of steps. But usually you have an integral over x hanging around, right?
Yeah.
Yeah, that's right. And the integral over x comes from your action, right? Comes from your Hamiltonian.
Yeah.
Right. So where is that here? So the integral would be this term here, right?
Yeah.
Right. So you have an expectation value. So that expectation value, all I've done is take a Fourier transform. So I can Fourier transform each term separately. Instead of doing them together, I can just say I have an expectation value over Fourier modes, and then I would need, e to the I k x, e to the I kx, right? 1 and 2 instead of, and I would have to do it for, this term. So I could have two separate terms here, and then I would have this term here. And the x for the second term would be 0 in this term, right? Okay, so good. Okay, so to get a delta function, I still need to have an integral over x somewhere. To write this in k space. So I can always eliminate one k variable with a delta function, right? This is what I wanted in the end. I don't know, I don't quite see it.
Yeah, I think it's hard to see right now.
Yeah.
So
let's just keep going, and I'll try to figure it out later. What I want is a final expression in k space that looks like this. So 2 over t, 2t over j. I got rho s in my notes. I'm going to take that integral over phi. So that'll give me a 2 pi. So I'm going to have something like 1 over 4 pi. So it should be 1 over pi. I've kept an integral over k. And I'm going to write that as a Bessel function. Right. For my Bessel function, J naught so the only point is I want to use that Bessel function as behavior at z equals 0. So 1 over 2 pi, 0 to 2 pi. E to the I z cos phi d phi. Right. So my k is going to go from, okay, slow. So I'm going to split this integral up. J pi into two pieces. One is the Bessel function, dk. This is all just a game. There's an integral where the numerator vanishes, and you basically just, throw that piece away. It's a constant asymptotically. So it's like if I was going from k0 to k roughly, I don't know, 1 over x, say, where x is the argument of that function. So if you plot these Bessel functions versus x, yeah, so J0 starts at 1 and then does some, I can't remember even what it does. Does it go below 0? I forget. But in some regime, this thing will be constant asymptotically. And then we're going to have some term that we integrate from 1 over x to some cutoff. I'm just doing this really rough, but where x is greater than, this behavior near 1. So somehow I have to define, some x that gives me some meaningful functional dependence. So it's going to be greater than this cutoff, which is, because it's in k space, somehow related to the UV, right, the lattice. And then,
so where is number 2?
this one?
Just, yeah.
Sorry, what?
Here's number 2, quick factor.
Oh, the 2 in front? It's probably still there. Oh no, sorry, it's the angular integral gives 4 pi, doesn't it? Oh, but I had 4 pi on the bottom. Yeah, it's very possible it's still there. Question mark? It's not the biggest problem with this derivation at this point. I'm trying to pull a log out of this. I don't know if it's going to happen.
When you say asymptotically, that suggests you've got some parameter that's going to infinity at some point.
Well, this one. It's when you move this closer to
Right. Okay.
1, and when you move it, yeah, so then that term's 0 somehow.
Yeah.
I basically just want to focus on this side here,
Right.
where I've defined some like IR cutoff, if you will.
Right. So I'm wondering if you've got a stationary phase approximation working in there, and that's what's giving you the missing step.
I don't think so, because everything's Gaussian, or I thought it was. But everything should be Gaussian, so.
Right. But you've got.
Oh, stationary. Oh, yeah, stationary phase would be where you just look at the maximum value, right?
Yeah, right. Because you've got variables collapsing into each other inside of exponentials, and that's
Yeah.
what we're calling code for stationary phase approximation.
Yeah, I wish I wrote down more than one line, but we'll work on it later. So up to factors of 2 and pi's. Do I have pi's still? The integral I want to look at is something like this. Okay, so J naught. Okay, so basically, I'm just going to throw that Bessel function away. And I'm going to leave it as dk over k. There, that's my log. That's what I was looking for. So I have it. I'm sure it's possible to do properly.
Okay, it's righty.
Exactly. So what is this? Log. So now I have log. I just got to get the sign of this correct. So it's got to be log of x over a. It's got to be that. Yeah. T over j pi log x over a. Okay, I have a. So when I put this in an exponential, I have a factor of 2 here. So I have an exponential of a log. That's what I want. So g of x, that's 1/2 t over j pi log x over a. So now I just have x over a to the minus t over j 2 j pi. Yeah, I think that's right. Yeah, okay, so this is generally what I was going for. So you have a log. Yeah, so you need to argue somehow that you have an integral that's a log. And that log gives you, because it's exponentiated, it gives you algebraic decay of the correlation function. Okay? So the point is that this looks like g of x x over, what am I trying to this looks like eta. That's what I'm trying to say. It looks like the anomalous dimension, because for a critical wave function, the form of g of x, which you derive, it should somehow look like 1 over, I don't know, r to the d minus 2 plus eta, right? And you're in 2 dimensions here. Yeah, so that makes sense. So eta is like t over 2 j pi. So the point is the correlation function looks, this is the when I showed you the simulation, this is the algebraic decay of the correlation function. That's worth doing properly, just not by me. So what that means is, somehow in the ground state you have, it's like you don't have long range order, as you saw in that snapshot at low temperature. You don't have full long range magnetic order, right? You have something that's got long wavelength fluctuations in it, even if you don't consider those vortices that we saw. And it comes from this. It comes somehow from this analysis. And somehow we need x, you got to be over the UV or whatever, you got to be large enough. So sometimes they call this quasi-long range order. And because there's a Mermin-Wagner theorem, the idea is that Mermin-Wagner says you don't have any true long range order except for strictly at 0 temperature. So when you raise the temperature in this XY model, you lose long range order, but you get this quasi long range order that has an algebraic decay of correlations. Okay? So there's no characteristic length scale. There's no exponential. There's no there's no e to the minus r over xi, z, whatever it's called. But so there's some paradox here, because we just measured the spin-spin correlation function, and that, remember I told you there's a transition, right? So at some point, the correlation function must be exponential. Okay, so this is missing that. We're not in that regime where we transition to exponential decay. So there's something not contained within this Gaussian solution. I think that's the point, right? This sort of way of doing long wavelength approximations to these K integrals is missing something, and you know what it's missing? It's missing the vortices. So to argue for exponential decay at high temperature, so you experimentally know, or you just, at some point you know that you need a paramagnet at high T. Number one, it tells you there must be some sort of phase transition, or at least a crossover, but there is a phase transition. And you need to include that in the theory somehow. Okay, so the problem is in the idea that theta I minus theta j, or theta x minus theta 0 is very small. Okay, that neglects the possibility of those vortices that we were looking at. And what we're trying to argue for is the fact that we need those vortices in order to describe the Kosterlitz-Salas transition. So a vortex is a configuration of the order parameter that winds around, like I drew up there, winds around a point in space. And you can draw that point like this. Whoa, that's supposed to be a point. Okay, so that's a vortex field. Right, so that core, vortex core as it's called, there's some energy cost. A gradient of theta will diverge, right, in the action. So you have to kind of worry about that, but if it's on a lattice, then that point isn't contained in, the space if you want, so. Diverges. Oh yeah, so that's the point, is the continuum. This limit here is actually not well defined. And what we tried to do here is a continuum theory, right? All this was the same philosophy as we've solved all of these propagators for in the continuum theory. So the lattice saves us from that, because the lattice removes that point. And we can talk about, vortices at points in space around, say, the dual lattice or something like that. So let's think of the lattice and remove that mathematical singularity with it. And I don't know how to draw this well. Let's imagine that we have some vortex in the center of some plaquette. And the orientation of the spins, okay, so let me draw that same type of vortex. So the orientation of the spins, maybe move outward from that vortex in a certain way. And we'll define the orientation with that angle, that variable theta. So if I'm at some point on this lattice, how do I want to do this coordinate system? I'll call it R. And R has an angle. I'm using theta for the variable, so I got to use I guess, phi for this angle. So we'll do it like that. Okay, so if I have a vortex, then the orientation of the spins is some multiple of phi. And I'll call that multiple n. So that's the charge or the strength or the winding number of the vortex. So I'm just describing the vortices, and I'll show you the energetics for the vortex. Okay, so as you're out here somewhere, you know, that angle is either, say, 1 times, you know, the n matters. So actually, let's draw a few. Charge, or what else are these things called? Winding number.
Multiplicity.
Multiplicity. Maybe strength, I don't know.
Is that like the topological charge?
Yeah, that's exactly what it is, yeah.
It shouldn't the multiplicity be the result of a circular integration around the vortex?
Yeah. I'm gonna show you the integral. I think it's fine. That's the solution to that integral of that term.
I'm just confused by theta being theta refers to one single spin, right, or not?
Yeah, that's the angle of a single spin. So let me just try it, mate. So if I have a vortex that always points like this, that should be n equals 1, right? So that those arrows are thetas, and as you move around there, theta is equal to the angle phi. No?
Okay, I've got a different understanding of that, that just, there could be 2 different ways of saying the same thing. It's like a phase singularity in the wave function.
Mm-hmm.
I mean, you can have like 1 branch cut, 2, or you can go around once or go around multiple times.
Yeah.
And that gives you a charge.
Yeah.
I think maybe you can treat that as a vector field. Right, so that gives you an arrow direction which changes around the phase singularity.
Yeah, so you can have, right, so this angle can, there's also a constant, right? So maybe I should say that. You can also have a constant angle offset.
I think you can
Let me call it a theta naught. So if you have a constant angle offset, so you have the n and the constant angle. So if I have n equals 1, and a constant angle offset, say pi by 2 or something like that, this would be 0. So my theta would be phi plus pi by 2. Then that would look like this, I think.
So would Skirmion be an example of one of these things?
No comment, but yes. And I can have pi. I can reverse all these angles, right? So I could have theta equals phi plus pi. And then that would look like this.
What's phi defined? Is phi just a coordinate?
Phi is the angular, so I've defined axis. So phi is just the angular variable. Around the vortex core.
Okay.
So I have to define this coordinate system's
with the vortex.
with the vortex core in the center, yeah, sorry. That's what I meant by this picture here.
Okay.
That's the vortex core.
And then but why is theta is necessarily multiple?
Well, so that I haven't given you the constraint yet. So that comes. I'm just drawing vortices. So I'm just drawing things that we've seen, and I'm going to give you the constraint. So the constraint comes from, as you know, it'll come from the action basically. Let me just keep drawing vortices. This is just qualitative, basically.
Google Skirmion, you'll find lots of nice pictures.
Yeah, they're better than these pictures, I'm sure. So one point when we looked at the simulations, you had vortex and anti-vortex pairs. So you could see these and these in there. You could, that program labeled the vortices as blue. But remember I said they occurred in anti-vortex pairs? So the anti-vortex of negative charge. So the anti-vortices of negative charge, so the n equals 1. How does this one look? It goes 2 in, 2 out, right? That's your anti-vortex, n equals 1, theta equals 0. So n equals minus 1. So theta equals minus. Is that right? Minus 5. I'm going to say, seems strange, but. You can have different charges on these things. I'm not actually sure I'm drawing the right charge now, so let me try another one. So this is n equals minus 2. So another one should look like this. And the bottom ones must go this way, I think. I'm going to combine these vortices and anti-vortices together. Actually, you can see that. So you can't create a vortex without a singularity. So you can't deform the far field of a vortex without leaving So say you had a far field, like a long wavelength configuration that was all pointing in one direction. You can't create a single vortex that obeys that ferromagnetic direction in isolation. So if I take that n equals 1 vortex and I put it here, and I try to bend all those lines of the vortex so that they match the far field, right? So it looks like this. Then I can say, well, down here, I have to bend these things up, right? Because I want my, as I go to the extreme, I'm bending my field lines up. You'll always have a singular, like, field defect that goes out to infinity for a single vortex. So you can't take that n equals 1 and just put it in a background ferromagnet without this single, defect line, if you will. And there's a discontinuity there. So here you'd have theta of 2 pi and 0, and there'd be some like discontinuity. So to get past that discontinuity, you do what the simulation does, and you add vortices in pairs. And you add one vortex of a charge with its anti-vortex. So how does that look? It's like you can take that far field configuration. All right, so out at infinity. Now you take your vortex, which you've deformed. And that's n equals 1, so I should be able to match it with the anti-vortex. Oh, did I do it right? Yeah, so it's coming down, right? That's right. This is the anti-vortex. Yeah, that's right, because the bottom's coming up, right, in the anti-vortex. So the bottom matches the far field, and you just bend the anti-vortex up like this.
Well, maybe.
Wait, I did something weird. Yeah, so these should come from, it's that picture there I'm trying to draw. These should come like this, right? So you can satisfy the far field, but you can still have topological defects which are created in pairs. And that's the point with vortices, right? That's enough vortex pictures. Let's figure out this n thing. If I don't do some math, it won't make any sense to me. So this is what you saw in the simulations, the vortex-anti-vortex pairs, right? And what happened in that XY model was they're created, and they can either proliferate above this transition temperature that I told you about, or they stay bound together, okay? So when they proliferate, you can see how they destroy the far field. It's like the Peierls argument, right? They proliferate and they're everywhere and they just destroy the far field tendency to order. And if they're bound, they don't destroy that far field tendency to disorder, even though there can still be sort of long wavelength physics on top of that. Okay, so let's try to figure out this n. So if we have a winding number n, so what we're doing is integrating. Yeah, so this will make more sense now. So I have a vortex center. I have a configuration, which is my field. That has a charge n. So I'm going to define a contour of integration. Around, which contains that vortex core, okay? So I'm constraining, or I'm defining the spin orientation to change by 2. That phi variable goes from 0 to 2 pi, so the spin orientation changes by 2 pi to the n. Two pi n. I think that's right, so. Okay, so in the continuum, in large R, the gradient of theta, has a uniform magnitude, right? So it's all pointing in the same direction. So I should be able to say, so it should be grad theta dot dl, where L is the length of that path, that contour C. This should equal 2 pi times the charge of that field, 2 pi n. If you enclose a vortex. So that's the constraint on the field, basically, if you have a vortex. So I define a vortex with that winding number, and if I do that integral, that's what I get out. I think that makes sense. So then I can solve this. So I have theta n phi. So again, a vortex core. Let me draw this better here. So I have a polar angle. Core. I have a unit vector for theta. All right, I have my so for phi. N phi. So I got to do this in polar coordinates. So the term that survives. So I'm taking a partial derivative. You need whatever the scale factors are part of the Jacobian. So I'm going to call that r. So it's 1 over r. Then I just have integral of that phi with respect to phi. What am I forgetting? The unit vector, probably. Okay. So then this will be like my vortex charge n over r and the unit vector for that coordinate system. Oops, that makes no sense there. Okay, does that make sense? So now I'm integrating that. Well, so I have this solution. So let me just look at the energy first. So I have a Hamiltonian for the XY model, say, or I have an action. I wrote that way back when. In cosines, but I derived it from the fields, so I can write it like I did the action, so it should be just grad theta squared, right? That's the energy of the vortex away from the core. So I have to just keep in mind, in this long wavelength theory, that's what this is. This continuum theory, maybe I should call it that. You know, the core would give you some sort of divergence. So I got two of these, n squared over r squared. Let's see if I can do this, J. So I'll do the angular piece, and then I got to have a limit of integration on the distance r. So I'll start from the lattice spacing, and I will just go out to the size of my system. I'll just call it L. So I'm just going to attach a length scale to this. This is like my UV. This is like my long distance. I got dr, r, that's from the Jacobian. And then I have 1 over r squared from this term here. Right. So now I have, again, a log. So pi j. I should have charge squared, n squared. Two, I get a factor of 2. No, do I get a factor of 2? I'm not sure about the factors of 2. Log L over A from the limits of integration. Plus, I would say, don't forget the core energy, plus the core energy, which we're just going to ignore. Okay, so the energy of a single vortex diverges logarithmically with basically the system size. Okay, and this A is your lattice constant. Maybe it's 1. Whatever it is, it's a constant, right? So it's okay, so it seems like vortices always cost us energy. So why would there be vortices? This is just a single vortex, right? You put a vortex in there, even if you ignore the singularity at the core, right? Just those field configurations, like just the fact that you have that field configuration costs you energy. The farther out you go, the more, when you do this integral, the more that that's affecting your continuum theory. So there's just no getting around the fact that there's an energy cost. So what's this argument missing? Entropy, right? So it's always the free energy. Just like the Peierls argument, just like everything we do, you have to worry about an entropy energy balance. So it's the entropy of the vortex which saves you, which allows these vortices to occur in some cases. So let's look at the free energy. Right, so the free energy is an entropy piece. These entropies, they're always a little, I think, hand-wavy in a sense. You need to know how many, say, positions or how many configurations of a vortex with a core at some position x, or how many different positions a vortex can occur in. So That's like a configurational entropy. You can either think of it as you have a system and how many possible positions can you put the vortex core, or how many microstates contain a vortex core at a certain position, either or. How many? Imagine I have an L squared lattice. It's square, it's L times L, it's 2-dimension. That's just basically, you know, L over A, right? Where L is measured in units of A, so it's just basically just L squared. It's just L over A squared. The entropy is log of the number of accessible microstates. So log of the number of microstates that has, so it's like log L over A squared. Okay, so it's just basically log L. And that's, you know, because of that configurational entropy, you're getting a balance with that logarithmic energy. And that's where the Koster-Salis transition comes from. So the free energy of a vortex is the energy of a vortex minus the core T S vortex that's probably pi j, that's probably right, n squared 2, and I have a T 2T yeah, something like that. Yeah, so it's the coefficient of the log. They're both logarithmic. If this thing is, you know, you have two terms here, how do you minimize the free energy? It depends on your temperature, right? So if temperature is high enough, then, like if T is large enough, then you'll minimize the free energy because of this negative sign when vortex positions occur everywhere, or vortices proliferate. Again, it's similar to the Peierls argument. And that proliferation of these cores will destroy sort of the far field. Right? So here you have like a far field order, and you have one vortex, or more accurately, you have something like that, that's a pair of vortices. But if you put pairs everywhere, because it's entropically favored, then you destroy that entire concept of a sort of ferromagnetic far field. And so that's what happens at high temperatures. And then your correlation length, consequently, is just the paramagnetic correlation length. Whereas at low temperatures, you minimize this with energetic constraints by minimizing the energetic defects, right? So then the vortices will basically, you know, only occur in tightly bound pairs, and we'll talk about that length scale, and essentially they don't proliferate entropically. Over 2, right? And that's the worst description of a Nobel Prize ever. But that's what Koster-Salis was given the Nobel Prize for, is this mechanism, basically.
So the proliferation, is it the creation of the vortex pairs, or is it does it mean the emergence of those, or more the unbinding thing? It means the unbinding, right?
Yeah, essentially, oh yeah, so that's a good point. Like here you don't see whether or not they need to occur in pairs, right? It's just an energetic argument. You could have a whole bunch of free vortices, but what happens is they're only created in pairs And then those pairs have I haven't derived it, but those pairs have a logarithmic binding potential that keeps them close together below the transition. And then above the transition, they're completely free, and they entropically occur everywhere. So you get more of them, and they unbind, I would say.
And the unbinding, so, I mean, when you consider the energy of a pair, then you'll see that it has dependence on the separation distance.
Yeah,
right?
yeah. That's what I haven't derived yet.
Yeah, we cannot have single vortices that are emerging in the system because the energy is, at least in an infinite system, it will diverge, right?
Yeah, you'll get even if you're out in the infinite far field, you'll get discontinuity here. Yeah.
Okay, so but this is basically the argument for why they appear in pairs.
Right.
So
Yeah.
this is visible from here, I would say.
Yeah.
But that's still this unbinding is not clear to me because
It's not. I don't think the binding unbinding is contained in this proliferation argument. It's just I think you need to know why you have binding. Like I think we need to do the energetic calculation of the binding.
we're gonna do this next time.
Well, I could do it now.
Oh, cool.
I don't know if I can do it in 10 minutes.
And you've got vortex pairs specifically rather than single vortices. Yeah. A single vortex carries this infinite energy penalty. So they travel around.
But if you're in the infinite temperature limit, you don't care about that energy penalty, is the other thing, right? So if you're truly in T equals infinity, I mean, everything's paramagnetic. So we're talking about kind of subtleties near the transition. If you imagine being below the transition and then warming above it, then you imagine that you're creating these in pairs so that you only have defects sort of locally, right? So those local defects don't cost you too much energy, and you have some thermal fluctuation, so the entropy gain allows, as long as it balances whatever that binding potential is, which I haven't calculated. Then as soon as you go above the transition, the idea is that entropically, now there's many different possibilities for vortex positions, and those pairs will just kind of disassociate and occupy all those different entropic configurations.
You expect the entropy or energy penalty to change as you pull the vortices apart.
Yeah.
Well, the energy for the pair increases as you pull them apart.
Yeah.
I mean, that's why it's a Twigler over quark confinement.
That's why, exactly. That's what I haven't calculated. So it's actually a Coulomb gas. So it's a Coulomb potential between the vortex and the anti-vortex.
But at which point do you say, I mean, the Coulomb force is infinite range, basically, as long as you do not have a screen.
Yeah.
And so
It's log
it's
x.
arbitrary that you say that, well, starting from this distance, they are independent. Because
Right.
they're actually not. It's just an arbitrary cutoff or like threshold that you say, well, starting from this, I will see them as independent. So, but
Yeah, so that, I think the interactions and all that Coulomb potential basically renormalizes that temperature, right? That's just some very sketchy TKT. So that's not the exact answer.
I mean, there's got to be an energy cost to creating a pair, right? And if pulling them apart also costs you energy, you pull them far enough apart, it becomes cheaper to generate another pair.
wait, what?
That's how
Entropically.
Entropically.
Yeah.
Like there's an energy cost.
Entropically, you
Pull them
want,
apart, it becomes cheaper to create a second pair, because then you can have two close pairs,
Oh yeah.
right? Instead of having one distant pair.
Yeah.
Right, and that's how quark confinement works. You yank a quark out, you create a meson, which
Yeah.
is a quark anti-quark pair.
should we look at the video instead of doing any more work?
And when you start, well, you need a certain temperature in order for air to emerge.
Yeah.
And then when you increase the temperature further, you'll get more and more of those vortex anti-vortex pairs, right? So the density of these pairs increases. Is this? I suppose that this is connected to the screening effect. That when you consider the vortices to be like a positive charge and the anti-vortices -1, and then you can think of it as a Coulomb gas.
Yep.
But then you can have those screening effects. But I do not have a complete picture of it. So
I don't think my derivation was a complete picture, which is. This is the. Okay, for everyone else who hasn't thought of this is the kind of simplest argument. Okay, energy entropy balance. We'll look at the Coulomb potential next time. So what do you want to do? You want to start at low temperatures?
Yep.
And warm it up, maybe? I don't know.
Yeah. I want to see the increase of the density of the pairs.
Oh, I think I destroyed this.
That would be cool. But I'm not sure what are we.
I don't know if you'll see it though, because
Yeah.
you have ergodicity issues in these things. So
What about boundary effects?
this is periodic.
Right, so that removes the boundary effect.
And if the thermodynamic limit, Costas Thales happens at the same temperature
You don't
for
have
open boundaries, yeah. Okay, did this work? Let's start low. So remember, what's happening here is you initialize it randomly. And so what it does is it quenches down into, vortices. It'll quench into some state where the vortices, there's just no, they can't get over their energy barriers, right? So the lowest energy state, presumably, is where these would find each other, right? Because there's field distortions. This is a vortex. That's the anti-vortex. So actually, that's a nice looking one. You can see. So this is a vortex of. It's like this one here, probably, right? Of constant theta offset. So you're actually circling that. You're actually circling that region here.
So you see two different things with different topological charges. The one on the left seems to be only one, and the one that's sort of.
Yeah, this one I would say looks like n equals 1, theta equals 0.
But the one that's sort of halfway towards the top right corner, that one looks like a 2.
It's either a 2 or it's where's my 2?
To right corner?
No, it's not out on the corner, it's roughly halfway between the centre and the top right corner.
So you mean the vortex or in
The blue thing.
This one here.
Yeah.
That's either an n equals 2 or I think it's a theta equals.
But when you look at the spins, when you just look at the
Oh yeah.
and just watch the winding when you go around, then it does not seem like a 2.
Well, you compare it with the one that's near the left-hand edge, and that looks like a 1.
Yeah.
Yeah, that one definitely looks like a 1, yeah.
So it
These two are going to annihilate.
actually did here.
Don't you love when that happens?
But no, the right one, the blue one on the right looks like, oh well, now it's more than 1.
There's a factor 2 in there, remember?
So 1 is above, temperature 1 is above the Costas-Thales transition. But I don't think it's enough thermal energy to get over the barrier, So even though this should become disordered, I think, the problem with these simulations is
You wait a bit,
you get
it might
stuck.
annihilate.
Yeah,
The
but
one goes wrapped around the back, then it'll be close to the blue one on the left-hand side.
the point is above the transition, they should proliferate. So if I just initialize it for a new random. So this is the same temperature, but I've started randomly, and now I'm doing Monte Carlo steps, and it stays paramagnetic, or it stays random, right? So the problem with all of the intuition you get from these things is that there's also this ergodicity issue. When you do your simulations for your computational assignment, also be aware of that. So this is vortex proliferation. This is, they pop in and out of existence, and then they move, and I don't know if it makes sense to say they dissociate, but they definitely can dissociate and combine with other vortices. I don't know if you can see it.
Mostly they just re-annihilate.
Mostly they just come back. There's still a potential, right? There's still a Coulomb potential keeping them together. So even though they entropically pop into existence, they'll tend to just want to come back. Yeah. And if you cool this down, right, that should be, what is this at 1? I'm not that far from the transition. So that's an exponential, but it's probably a weak exponential. What if I go back down to low temperature? Probably all that'll happen is they'll just freeze in whatever configurations I have. No, maybe not. I'm not 100% sure this applet works the way I think it does either. Is there less vortices? I don't know.
It's pretty stable.
Yeah.
Well, no, maybe it's folding out now a bit.
Of course, look at your Monte Carlo steps. We're not even at 1,000 yet, right? So this isn't exactly equilibrated. It takes, I don't know how many, it takes a long time to equilibrate in principle. Okay, well that was a good waste of time. This is online somewhere. I don't know where it is, but just Google XY Java applet. So what I'll do next time is, can I reinitialize this? So let me calculate this Coulomb potential next time. Talk a bit more about the energetics. Then I'm going to write down the RG recursion relations for the Coulomb gas, which is in your assignment 5, although I'm not going to derive them. I just want you guys to like play around with the fixed points. And then that's pretty much it. So we'll spend another class on that, on Causa Salis, trying to figure this all out. And then the last class, we'll just do something else fun on entanglement. Okay, so next week's our last week. Then we're done.